Astronomers unveil the most distant galaxy yet discovered. On May 30, 2024, astronomers announced a significant discovery. Using observational data from the James Webb Space Telescope, they successfully detected a galaxy with a redshift value as high as 14, located approximately 13.5 billion light-years away from us. This galaxy, dating back to less than 300 million years after the birth of the universe, is an exceptionally ancient entity in the cosmos. Since the launch of the Webb telescope, astronomers have been dedicated to exploring the traces of the first galaxies in the universe. To this end, they formulated the Advanced Deep Extragalactic Survey (AIDS) program. In the initial phase of the program, the Webb telescope observed a region of the sky in the direction of Fornax, located near the Hubble Ultra Deep Field. In 2023, the Webb telescope conducted a 5-day deep imaging survey of this region as part of the AIDS program. During this observation, astronomers discovered 12 very faint spots with redshift values generally higher than 11, indicating that their light travel distances are all beyond 13.4 billion light-years, making them candidates for early galaxies. Among these candidates, 3 galaxies stood out with redshift values as high as 14, corresponding to extremely distant locations. However, one galaxy with a redshift of 14.4 was significantly brighter than other high redshift galaxies, which sparked great interest among astronomers and made it a primary observation target. To determine the exact distance to this galaxy, astronomers conducted more detailed spectroscopic observations. In January 2024, a research team used the Webb telescope again to photograph it for about 10 hours, and finally obtained its spectroscopic data. The data showed that the galaxy's redshift value was 14.32, breaking the previous record of 13.2 for the most distant galaxy, and becoming the farthest known galaxy to date. When we talk about the distances of remote celestial bodies, astronomers often use redshift as a tool for measurement. Simply put, the larger the redshift value, the farther away the celestial body is from us. So, what is redshift? To answer this question, we first need to understand a basic concept, Fraunhofer lines. Taking the sun as an example, when sunlight undergoes dispersion processing, it exhibits light of different colors. If the observational equipment is sufficiently precise, we can find many dark stripes among these colored lights, which are Fraunhofer lines, named after their discoverers Fraunhofer and Fay. Fraunhofer lines are essentially absorption lines of elements, meaning that when light passes through certain elements, these elements absorb light of specific wavelengths, leaving dark stripes on the spectrum. Different elements absorb light of different wavelengths, so these dark stripes serve as fingerprints of elements, imprinted in light. Spectral redshift is the shift in the position of Fraunhofer lines. Normally, Fraunhofer lines appear at fixed positions in the spectrum. However, when the wavelength of light changes, such as being stretched out, these dark lines will appear in the stretched-out wave spectrum during display, looking as if they have moved towards the red end of the long wavelength band. This phenomenon is called spectral redshift. Moreover, the farther the dark lines move, the farther away the celestial body is from us. The redshift value is calculated as z equals lambda minus lambda 0, divided by lambda 0, where lambda is the observed wavelength and lambda 0 is the wavelength in a rest state, i.e. under laboratory conditions. For example, if we observe a spectral line emitted by hydrogen atoms in a distant galaxy, the wavelength lambda 0 of this spectral line in a rest state, which is a specific line in the Balmer series of hydrogen atoms, is 486.1 nanometers. However, due to the galaxy moving away from us, the wavelength lambda of this spectral line we observe is stretched out to 490.0 nanometers. Substituting the known lambda and lambda 0 values into the formula, we obtain a redshift value of approximately 0.0080 for this galaxy. Meanwhile, according to Hubble's law VF equals hc times d, we can also use this redshift value to estimate the approximate distance to this galaxy. Let's return to this distant galaxy. Apart from its great distance, the brightness of this galaxy also surprised astronomers. Based on previous observations and predictions, early galaxies in the universe were generally small with a limited number of stars, so their brightness was not expected to be high. However, this galaxy is brighter than expected, and the light source mainly comes from stars rather than the accretion disk of a central black hole. Additionally, observations by the Webb telescope also detected traces of oxygen elements, indicating that a group of stars within the galaxy have already undergone death. This discovery suggests that galaxies at the beginning of the universe may have grown much faster than we anticipated. This galaxy, formed in less than 300 million years, provides valuable clues for understanding the rapid growth of galaxies. In the future, observations by the Webb telescope may discover more such galaxies, deepening our understanding of the universe.